So up until now, we have looked at various control volumes and different effects of compressibility versus incompressibility, steady flow versus unsteady flow, uniform flow versus non-uniform flow. But in each of those cases, we were looking at a steady control volume or a stationary control volume that we put into a pipe, or I don't remember what our other examples were. But now we want to look at a moving control volume. And the motivation behind that is as follows. Let's say that we have an airplane that's flying through the air, and we want to analyze the mass and fuel flow rates into that engine. So to be more explicit, let me draw the engine here. Looks something like this, let's say. And we know that, at least from the perspective of the airplane, that there is air coming into the engine. That is, air gets sucked into the engine. Air gets blown out of the engine at some speed. And then we have some fuel. Oops. Fuel. Let me spell that right there. Fuel going into the engine. So we have air coming in the inlet, fuel being pumped into the engine, and at the outlet we have air plus the combusted fuel as well. And we'll give it here in just a second. We'll give the conditions on all of these flows, and the object is going to be, given what we know about the air coming in and the mixture coming out, how much fuel are we adding to the are we pumping into the engine? Now, if you consider an airplane flying through the air, or if we consider this engine that's, whoops, let me do this in red here. This engine moving through the air, it's pretty clear that if we had some stationary control volume with the engine moving through it, right? At some point the engine is here, and at some time later the engine is here, and at some time later the engine is here. All of a sudden the problem becomes really difficult because we don't know, well, do we analyze the system when the engine is in the middle? And if we do analyze the system when the engine is in the middle, do we have to take anything else into account? How are we going to deal with the fact that the engine itself isn't stationary? And the answer is as follows. The answer is we don't do this. The answer is that we create a moving control volume that conforms to the engine itself, which I'll draw up above here. So now the control volume and the engine are moving along together, and so we have a different question, which is now how do we deal with the fact that the perceived inlet flow or the perceived outlet flow or even the perceived fuel flow are different whether you're moving along with the flow or not. And to deal with that, we have to rewrite the Reynolds transport theorem to deal with relative velocities. So before we had the Reynolds transport theorem was d dt of our control volume, the integral over our control volume of rho b dv plus the integral over the control surface of rho b v dot n hat dA was all equal to the change of capital B, whatever extensive property we're looking for the particular system. Now, if we look at a moving control volume, I'll go back to red here. Let's say that our control volume is moving, in this case I'll draw it to the right, doesn't really matter, at some velocity, and we'll call it v sub cv. That is, it's the velocity of the control volume. Then any any fluid particle that is moving with respect to this control volume, in particular that's moving across, let's say, across some boundary, well, we call that velocity vector v, as we have before. But we know that we can write v, the absolute velocity, is equal to the velocity of the control volume plus what we'll call w, which is the relative velocity of the fluid with respect to the control volume. This is exactly what you did in your dynamics class when you were dealing with translating or rotating systems. And we can rearrange this to show that the relative velocity, of course, is equal to the absolute velocity minus the velocity of the control volume. Now here's the nice part. The nice part is that when you reconstitute the Reynolds transport theorem for a moving control volume, it turns out that only the relative flow with respect to the control volume or the control surface matters. I'm not going to go into all the details and work through the whole derivation once again. I think it's pretty clear that when we realize that the Reynolds transport theorem is basically a relationship between what's going on inside the control volume and how fast whatever characteristic, whatever property we're looking for is coming across the control surface, that only the relative velocity across that control surface is really going to matter. So if that's the case, we can rewrite the Reynolds control theorem like this. And I'll just do it here for completeness. So the only change I made was, instead of using absolute velocity v, I've used relative velocity w. Now for a stationary control volume, well, this works out just fine anyway, because for a stationary control volume, the velocity of the control volume is by definition 0, and so v and w are the same quantity. And so it's easy enough just to remember that, well, this equation is actually more universal than the one above, and it's not even really that much harder because it applies to both moving and non-moving control volumes just the same. So let's go back to our problem that we had above, and we're going to redraw it here so that we have some space. We have our engine. And from the perspective of somebody standing on the ground, right, from the perspective on the ground, the engine is moving to the left. And let me see how I'm going to draw that. I'll put that up here. The engine, or the whole airplane, is moving to the left at 971 kilometers per hour. And from the perspective of the ground, the exhaust is coming out the back at 1,050 kilometers per hour. Now, the frontal area of the jet engine, somehow the person on the ground realizes that the frontal area is equal to 0.8 square meters. Their entering air density is 0.736 kilograms per cubic meter. And let's see, the exhaust area here is 0.558 meters squared. And the exhaust gas density, which I'll just write down here, is equal to 0.515 kilograms per meter cubed. All reasonable numbers for a modern jet airline. So the first thing we have to do is figure out what our relative velocities are. And to do that, we will well, the first thing we have to do is draw our control volume, which we've already discussed, which will look something like this. It'll just include all of the air as it's going through the jet engine, like that. And we see we have three control surfaces that we need to deal with. One is the inlet, one is the outlet, and one is the small one where the fuel is coming in. Now, next we need to determine what our relative velocities are. And to do that, we identify what we have for each of the inlet and outlet velocities. So looking at the inlet first, I'm going to put a 1 here so that we can keep track of things. Looking at the inlet first, I seem to have lost my mouse. There we go. The absolute velocity from somebody standing on the ground, v, is just equal to 0. And, well, we can draw, if we want, we can draw a coordinate system, and I guess we will put, we'll put x to the right. And so, let's see, the absolute velocity is 0. The velocity of the control volume is going to be equal to the speed of the plane, which is, I've forgotten what the speed of the plane is, 971 kilometers per hour. And it's to the left from the viewpoint of somebody standing on the ground, so it's in the minus I hat direction. And so therefore we can write W is equal to, go back and remember this equation here, W is equal to the absolute velocity minus the velocity of the control volume. So W is going to be equal to 0 minus 971 in the minus I direction. So it's going to be 971 kilometers per hour in the I hat direction. At point 2, or at the outlet, cross-section 2, we know that from the perspective of the ground that the exhaust is going to the right at 1050 kilometers per hour, and that's in the I hat direction. The velocity of the control volume, again, is 971 kilometers per hour, and that's in the minus I hat direction. And so W is going to be equal to 1050 I hat minus 971 minus I hat. And so it's going to be equal to, well, we get a minus and minus, so we get a plus. And so we end up with 2021 kilometers per hour, and for completeness, in the I hat direction. So when we write out the equation for the conservation of mass, which we get from the Reynolds transport theorem, we know that the rate of change of mass in the control volume is equal to the rate at which mass crosses the control surface. And because we're using the moving control volume, we have W, the relative velocity, as opposed to V, the absolute velocity. The problem is steady from the perspective of the moving control volume. That was the whole point of making the control volume move along with the flow, is that from the standpoint of somebody sitting on the airplane, the flow is a steady flow. And so we get a 0 on the left-hand side, and therefore we get that the rate at which mass crosses the control surfaces have to all add up to 0. So we have a third. So we can take this control surface and we can expand it out for the three control surfaces, or the three areas that we know of. On the left-hand side, at the inlet, that is, we have. Let me rewrite this so I don't. So, knowing that the right-hand side equals 0, we'll write it as the integral over the control surface of the density W dotted with n hat dA equals 0. So now we just need to expand the integral for each of the control surfaces that we know of: the inlet, the outlet, and the fuel inlet as well. So for the inlet, we know that the integral, and I'll just put a 1 because we called that region 1. The density, the integral over that of the density at region 1 times W dotted with n. Well, W for region 1 is 971 in the I hat direction, but the outward pointing normal points in the minus I hat direction given our coordinate system. So this ends up being minus 971 integrated over the area, plus at the outlet we have the density at the outlet times W dotted with n hat. Well, W for the outlet is 2021, and it's in the same direction as the outward pointing normal, so when I is dotted with I, you get 2021 again, integrated over the area. Plus we have a third control surface where mass is coming across, and that's where the fuel is being injected. And the question has asked us to find the mass flow rate of fuel into the engine. So we know that this first term is going to give us the mass flow rate of the air coming in. We know that this is going to give us the mass flow rate of the air going out. And so the last term is just going to be the mass flow rate. We'll call it m dot fuel coming into the system. And that's all going to be equal to 0. But the question then is this a plus or a minus? And we have to remember again our convention, which is the mass is coming into the system, and so it's going in the opposite direction as the outward pointing normal, and therefore we get a minus sign here. Now, assuming uniform flows, we can write each of these integrals as the average velocity times the area. Actually, it's the average velocity times the area. It doesn't have to be a uniform flow because we're talking about average velocities. So on the first one here, we get, let's see, what was the density coming in again? We get 0. Let me write it in this form again. We get rho 1 times area 1 times our minus 971, because that's our W dot n term. And here we get rho 2 A2 times 2021, and all that minus the mass out of the fuel coming in is equal to 0. And now we start plugging in numbers. We get 0.736 kilograms per meter cubed times the area, which is 0.8 meters squared, times minus 971 kilometers per hour. We get rho 2, which is 0.515 kilograms per cubic meter, times 0.558 meters squared, times 2021 kilometers per hour, minus, well, all of that's equal to m dot fuel, because we'll just take that to the other side of the equation there. And when we go and do the math, let's see, so let's plug in some numbers. I got my trusty calculator here. We get 0.736 times 0.8 times minus 971, and I get here minus 571. Let's see, doing our units. We got to convert a kilometer here to meters, so we got to multiply by 1,000, We get 571,000, and then all of our meters cancel, and we get kilograms per hour. And the next one we get, let's see, 0.515 times 0.558 times 2021, and we get 580 times 1,000 again for our conversion, 580,000 kilograms per hour. And we add those together, and that gives us, it looks like, 9,000 kilograms per hour. So m dot was the rate at which the fuel was coming in. We already took into account the fact that it's coming in here, so we have the negative sign here. So m dot is the rate at which fuel is coming into our system.